Tyler.
So introduce yourselves.
Gabriela, this is Tyler, and our project is the airflow, temperature, environment, which can be implemented on different occasions. I saw online people were have a similar setup for like a greenhouse or like even like a room temperature control or whatever. And our system requirements, which interface a temperature sensor, our board, our Arduino board, 12-volt computer fans, and liquid crystals. We wanted the fan to oscillate according to the temperature of the sensor. So our minimum was, we decided it should be 298K, maximum 302K. And the display should read the current temperature. And for specifications, specifically, we wanted the temperature to provide accuracy of plus minus 1 at 25 and plus minus 2 over the range of the temperature sensor, which we had already tested in our previous project 3, so we knew that worked already. And the LCD, we wanted it to display the different temperature ranges, Kelvin, Celsius, and Fahrenheit, on the push of a button. So, oh yes, the fan, like I said previously, the minimum should be 298, and so the fan would turn on when the temperature was 298 Kelvin, and it would turn off when it reached 302, and here are the different temperatures and Celsius and Kelvin. And so we decided a duty cycle for the process modulation that we use to control the fan oscillation to be 20%, from 20% to 100%, where 100% would be like the fan's maximum oscillation.
So 20% kind of has something to do with the integration issues.
And here's our overview of the system, high level, which is the temperature sensor, senses the temperature, and then it reads the voltage, sends it to the MA328P. The ADEC converts it to a digital value, and then that information goes to the screen and the PC fan. Wait, the screen. The screen and the fan. And so we need the transistor to supply current for the fan and a 12-volt power supply.
All right, it's just a little difficult to see, but so this is the hardware. I mean, this is the Atmega, and this is the LCD, and it's kind of and this and then it's the temperature sensor, and that's kind of like recycled from the LCD is basically from the tutorials, and so there's no difference between those. That was kind of recycled. The temperature sensor from our project 3 and a button to control the LCD outputs. And then for this particular final project, on top of our previous project, we added the 2 fans, which operate off of NPN resistors, and the 12-volt power supply. And the software flow basically, it originally was basically just this left half, but we included this, which has the pulse width modulation conversion from the digital value to the ADC, and then that went into an output compare controller that controls. If it's basically, we chose that for this RPM basically stands for a variable that stands for the output compare register, and so we chose for value under 60 to be negated to 0 because friction wouldn't allow it to run under that, and we figured it wouldn't really be as beneficial as you would think to have it go to not like over 60 and then drop it down in order to have it run. And then values between 60 and 255, which is the max OCR value, would just straight up get the pulse pulse width modulation conversion value, and over 255 would just be the max, and it cap it so it wouldn't overflow. The status for the integration, basically we had some issues with the transistors because most of the transistors that were provided through lab can't handle the bias currents that we would be dealing with the 12 volt supply and the fans, which run at about 0.3 amps each. So that exceeds most of the transistors that we work with. So we ended up working with medium power transistors. Initially, we were going to use MOSFETs, but the capacitive loading values caused too much noise for the fan to really have the accuracy of the duty cycle ranges that we wanted. And like I said, the controller for the resistor controlling the friction and overflow values. And so I guess we'll go over here. We wanted to use a voltage divider initially, but a voltage divider would produce heat on the transistor or the amplifier that we're using, but just by being in close proximity to the sensor, it's not sensitive enough to detect that. So we need something like the hair dryer to create more of an ambient type of temperature. But so it's approximately 297 K right now, so it wouldn't run until it got to about 298. And so right now I have the sensor over here, and it would kind of depend. It kind of depends. If I put it right under it, it would easily max out. But by having it over here, this helps it keep within that operating range. So the airflow keeps it from maxing out, but this keeps it from going too high or too low. And this keeps it from going too high. This keeps it going. So. It's a little hard to see, but so this is the fan that's sucking air in. This is the fan that's sucking it, that's blowing air out, and you can feel it's hot air being blown out. And the blue LEDs on this indicate the different level of duty cycle. It gets brighter as it increases and gets dimmer as it decreases. And right now, it's just over 298, so it's a pretty low duty cycle at the moment. I could probably move it. I could probably move the sensor more directly under it. Now it's getting closer to about maxing out. It's about 301 Kelvin right now. And that's the reason why we have such a small range of degree variance, because we couldn't create an environment that would make it go much higher than that. So then, if I were to shut it off, you can kind of hear it stepping down in duty cycle, and the LED getting dimmer as the temperature decreases.
And the LCD just says what the temperature is?
Yeah, and I have the button left over from the previous project, which does convert it to Celsius as well as Fahrenheit. So it should just about shut off. It's warmer in here than it was in my room when I was. But yeah, so eventually it's gonna shut off. It's just the threshold of the 20% pulse width right now. It's kind of hot. I don't know. I don't know. It went under the 298, so it shut off.
Okay.